First problem we're going to look at is when we have a sample and we want to compare it to a population where we know the population mean and the population standard deviation. For this example, I'm going to use some numbers that are a little bit made up, but I've looked some of them up online, so they're about right. I'm going to compare average SAT scores for the mathematics section of the SAT overall for the general population of students who take that examination and compare it to a group of sociology students here at the University of Maryland. Here's some of the information we know. Our population mean, our mu sub y, is equal to 500, and our standard deviation of the SAT score in the population is 100. Now, those two pieces of information are unusual to have. We typically don't have either the population mean or the population standard deviation. They're actually very important pieces of information that allow us to calculate a z-score here instead of a t-statistic. We have a sample of UMCP sociology undergraduates, and they had an average score on this SAT of 600, and we talked to a sample size of 150 individuals. We observe here that there's about a 100-point difference between UMCP undergraduates and the average for the math score, and we'd like to know if this group of UMCP undergraduates is statistically significantly different from the average mathematics grade. I'm going to set my alpha level equal to 0.05, and we're asking the question using the null hypothesis: is one population mean minus an estimate of the other equal to 0? Or is the alternative hypothesis correct, where this difference is not equal to 0? Let's go ahead and look at a quick graph and see if this will help us understand how to do this problem. Here's what a sampling distribution might look like. We know that our sampling distributions are approximately normally distributed. We know that when we convert any score to z-scores, our mean will be equal to 0, and therefore our population mean of 500, when converted to a z-score, is 0. We also know that if we move out 1.96 standard deviations or standard errors on one side and minus 1.96 on the other, that we capture approximately 95% of the distribution in the middle. That is, this shaded in area is approximately 95% of that normal distribution, and the area that falls in the tails is 5%. Now we have a score for the sociology students of 600. 600 obviously is larger than 500, but we want to know if it's statistically significantly greater than 500. So somewhere up in this region of the graph, we're going to have our score of 600. And what we're going to do is we're going to convert 600 to a z-score, and if it exceeds 1.96, that is if it's out here in the tail of this distribution, we're going to reject the null hypothesis. And if it's between 0 and 1.96, we're going to fail to reject the null hypothesis. Let's go ahead and look at our z-statistic. Our z is going to be equal to our population mean minus our sample mean divided by our standard deviation for the population divided by the square root of our sample size. And plugging our numbers in here, 600 minus 500 divided by 100 divided by the square root of 150, and this is equal to 100 divided by 8.165, and therefore our z-score is approximately equal to 12.23. So we can see from this problem that the 100-point difference in the average SAT score, comparing the population of students who took the Math SAT nationwide to a select group of students at the University of Maryland in the sociology program, is statistically significantly different, with the Maryland students scoring higher than expected.